So today we're going to talk about maps from a compact Riemann surface to the projective space, and this will generalize to maps from algebraic curves over any field, not just over C, to projective space. So we want to give three ways of viewing this. We want to view these maps in terms of tuples of metamorphic functions. We could also view them in terms of linear systems, and the third way is to view them in terms of line bundles. But in this video, we're just going to discuss the first viewpoint. So how holomorphic maps from X to Pn are in bijection with just tuples of metamorphic functions on X. So given a holomorphic map phi from X to Pn, how do we get a tuple from that? To understand this, let's look at the case when phi is a map from X to a affine space, Cn. Do you see why any such holomorphic maps must be of the form f1 to the fn, where fi are holomorphic on X? And by this I mean that there will be holomorphic functions fi on X such that at every point p, phi of p is just going to be equal to f1p to the fnp. Right? This is the point of c to the n. So what are these fi? Well, on Cn we have coordinate function t1, tn, and these fi's are just gonna be the pullbacks of this coordinate function. Okay, so now you might want to imitate this argument. You might say that, alright, then if I have a map phi, holomorphic map to Pn, then I can also pull back. I will let fi be pullback of the coordinate function xi on Pn. And so then the map phi will correspond to the tuple f0, fn. Okay, what's wrong with this argument? Well, the problem here is that even though we often write coordinates of point on Pn as x0, xn, these are actually not coordinate functions. They're not even functions, well-defined function on Pn. So taking their pullback does not make sense. However, their ratios are coordinate functions on affine pieces. So for example, on the affine piece x0 not equals to 0, the ratio xi over x0 are indeed coordinate functions, and these are metamorphic functions on Pn because they are holomorphic on an affine open. So the pullback fi here are going to be metamorphic, not holomorphic, but metamorphic functions on X. So that's how, given a holomorphic map phi from X to Pn, we construct an n+1 tuples of metamorphic function on X. This is to check that this is actually well defined. Now conversely, suppose that we have a tuple of n+1 metamorphic functions on X. How do we construct a holomorphic map on the whole of X? So notice that this map f0, fn, it's going to be well defined. We can evaluate this fi at any point p that is not a pole of any of the fi and not a common zero. So now what we need to deal with is that there is a case when either p is a pole of some fi or p is a common zero of all of the fi, and the idea is that we just take a local coordinate center at p, so some z, and then we divide by a sufficiently large power of z so that p is not a pole of any of these, and it's also not a common zero. So let's take some example. Now, because we only care about vanishing of the fi at p, so without loss of generality, we can just assume fi's are just power of the local coordinate z. Okay, so for example, let's say the obstruction, let's say fi is of this form, so that the problem here is that p is a common zero of all of the fi. Remember, this z is the local coordinate center at p, so z at p is 0. So the problem here is if we evaluate all of this at p, we get 0, 0, 0, which is not a point of the projective space. Then no biggie, because we can just divide everything by z squared, right? So we get 1, z to the 4th, all right? And then, so now under this coordinate, p is going to map to 1, 0, 0. Now, let's look at another example when the problem is p is a pole of some fi. So let's say fi, f is 1 over z squared, 1 over z to the 5th z. Right, so now we have the problem if we evaluate this at P, we will have two poles. We'll have a pole here and here. So when we want to cancel this pole, we can multiply with z squared, but that doesn't cancel this pole, so we should multiply with z to the fifth. Right? If we multiply with z to the fifth, we get this. And so under this coordinate, we see that P maps to 0, 1, 0. Observe in both cases, what did we divide all of Fi by? So in the first case, we divide everything by z squared. In the second case, we divide everything by 1 over z to the fifth. So in both cases, we are dividing by a power of z to the minimum, right, exponent. In other words, we divide all the Fi by a power of z to the minimum of the order of vanishing at P of the Fi. After we do so, then the order of vanishing at P of all the Fi now is must be greater than or equal to 0, and so that there is no pole, right? And for exactly one Fi, for some Fi, let's say F naught, we'll have that the order of vanishing at P of that is going to be 0, so that P is not a common 0 of all of these new coordinates. And that is how we reconstruct a holomorphic map from a tuples of n metamorphic functions on X. And it's easy to check that two different tuples give the same map if and only if they differ by a metamorphic function on X.